All right.
Yeah, just go ahead.
Great. Yeah, so today we'll talk about Beilinson-Bernstein localization. There are many proofs of this, and Roman Bezyrevnikov at MIT has a big document with like a list of a bunch of proofs. I'm going to be presenting a proof due to Bezyrevnikov, Braverman, and Posteletsky. Although their argument is based off of work of Kajdan, work of Lamont, and work of Bernstein. So I guess this proof kind of has a long history. So I want to start by, I guess, just giving a statement of Beilinson-Bernstein localization. So it's going to be some kind of geometric interpretation of representation. So let me talk about what representations I'm considering. So I'll have G, a complex reductive group. We'll take B, Borel. Then we can write X is G mod B is the flag variety, which is going to be some smooth projective variety. Great. And so Beilinson-Bernstein localization is going to posit an equivalence between two categories. The first category is related to the category of U of G modules. So G here is the Lie algebra associated to that Lie group G. U of G is the universal enveloping algebra, but we're not going to be considering the entire ring U of G. Instead, for each central character of U of G, for each character of the center, we're going to define a kind of ring U sub chi as UG modulo the kernel of chi. So modules over UG encode representations of the Lie algebra G. Modules over this ring encode representations where the center acts by this character. Center always acts by some character. The center always acts by some character in irreducible representations. So we're kind of looking at the pieces of the representation where the center acts by this character when we look at this ring. Great. So then, so this is now part of the setup, and now we have to make some kind of annoying row shift conventions. So I'll take N in the Borel, unipotent radical. And H is like the universal Cartan, so you can think of it as B mod N or like as a maximal torus. And then let W be the Weil group. So the Weil group has some kind of usual action on H, like the dual of the Lie algebra of H, but we're going to kind of shift it slightly. And so I'll use this little asterisk to mean the following like row shifted action of the Weil group. So we take the usual action on lambda minus rho, and then we add rho, where rho is the kind of half sum of the positive groups.
In like our SLN example, so B is either lower or upper triangular matrices.
Yeah, so
Yeah,
in our SLN example, so B will be the upper triangular. Oh yeah, unipotent radical. This just means triangular matrices where the diagonal is all one. So unipotent, like a unipotent matrix has like all eigenvalues roots of unity. And so this is like all the upper triangular matrices with diagonal one. And then I guess the nice thing about the unipotent radical is I can write a Borel matrix as something in like the maximal torus, which is like diagonal matrices times the unipotent radical. And that's pretty easy. Like I just take the diagonal entries of my matrix and then I find some like unipotent thing. The unipotent thing has diagonal entries all one, but it's allowed to have a bunch of upper triangular entries. So then when I multiply it with something in the torus, which is allowed to have any diagonal entries, I can kind of get anything in the Borel.
So when you're looking at this U chi, if chi is 0, for example, then you're only looking at representations where the center acts by 0, not where it acts nilpotently.
Yes. Yeah.
okay. And B mod, sorry, so H is B mod N. So that, but that's different to the torus.
Well, the reason is that if you take the diagonal matrices, they're not the only torus in B. conjugated by any element of B. So there's not a unique N is unique, but H is not. So by doing it this way, it becomes canonical.
Okay.
Yeah, so that's a good way of saying it.
You end up having to choose a look. Grid.
Uh-huh.
Grid. I don't know, he hasn't done it yet. But there, yeah. You choose a look. But like there's a copy of H and B because it's a semi-direct product. But it's not unique.
Yeah, I'll say like, in some sense, maybe the first part of my talk will be the most boring, where I like get all of this kind of Lie group notation out of the way. Which is the slightly unfortunate thing about giving a talk on a subject like this. But I think the bulk of the talk will be mostly about the example when, the bulk of the talk will be about a theorem of Bernstein, which proves a version of Beilinson-Bernstein localization when X is Pn. And so I have to explain what that means because Pn is almost never a flag variety. So I'll have to explain like what Beilinson-Bernstein localization for Pn is. But most of the proof works for Pn. And then at the end, I'll say how Bezerevnikov, Braverman, and Postoletsky kind of made it work for these general flag varieties. But hopefully, hopefully like most of the talk won't require much like knowledge of the theory of like Lie groups, which is convenient for me because I don't have much knowledge of it. So the reason I was mentioning all this is because there's a theorem of Harish-Chandra, the Harish-Chandra isomorphism, which helps us describe characters like this. And in particular, Harish-Chandra says that these characters chi are in bijection with Weil orbits, where I'm using this kind of like row shifted action. Weil orbits in the dual of H. So I'll write chi subscript lambda for the character associated with lambda. So there's this kind of bijection, and so and now I'll make one last like row shifted notational convention, and I hope I've shifted the rows in such a way that I never need to like write row again. The last convention I'll do is when I write U subscript lambda for lambda in H star, you might think that I'll refer to like U subscript chi lambda, but actually I'm going to define this to be U subscript chi lambda minus rho. And I think by incorporating a row shift here, I won't have any row shifts anywhere else in the talk, which is good because it's kind of annoying to have to keep track of this. So I get this ring, U lambda, and then this ring is kind of going to be the subject of Beilinson-Bernstein localization. Great. And so the next thing we have to discuss are twisted differential operators. So Beilinson-Bernstein localization is going to try and find some geometrization of the category of U lambda modules. And the way you're going to do that is with twisted differential operators. So there's this usual algebra EX, like the usual algebra of differential operators on this kind of smooth projective variety X, but we're going to have a kind of slight replacement up. So instead of dx, I'm going to be considering d lambda defined as follows. So d lambda, maybe I'll call it the ring of twisted differential operators. And it's defined as follows. So before we were talking about this kind of Borel-Weih-Bott theorem, which part of the Borel-Weih-Bott theorem is it tells you if you have an integral weight lambda, you can define a G equivariant line bundle on X. So L lambda is some line bundle on X. And then I'm going to define D lambda to be the differential operators of this line bundle, where, what do I mean by the differential operators of a line bundle? This definition is due to Grothendieck. It's a sort of inductive thing. So you say that a differential operator of order 0 is a function or maybe I'll say is a multiplication by a function. So if you have a function f, you can take a section of L lambda and multiply it by f, and you'll get another section of L lambda. So this is what I mean by a differential operator of order 0. And then there's some kind of inductive definition where then a differential operator of order at most n is some endomorphism L of L lambda with the commutator LF for any function f being a differential operator of order less than or equal to n minus 1. So this is some, I think it's due to Grothendieck originally, some inductive way of defining the ring of differential operators on some sheaf. So
the differential operators of order 0 is that O of x still?
Yeah. So differential operators of order 0 are the functions in O of x. Yeah. So L lambda, because it's a line bundle on x, is like a sheaf of OX modules. And then like a differential operator of order 1 would be something like differentiation with respect to some vector field. And then like if I have like differentiation with respect to a vector field V, and I commute it with f, this commutator will end up being the function del V of f, maybe up to a sign. And I guess this was kind of the observation behind like this recursive definition of differential operators.
So L is a map of what? Like
C linear, yeah. So L in N C L N. Yeah, so it's like C linear endomorphism.
And are you working like on some open set U or?
Yeah, so this d lambda will be a sheaf, and so on every open set U, like here I should mean like f in OXU, here I should mean like L and NC L lambda of U. Like d lambda is a subsheaf of this sheaf. And so L is like going to be a section of this sheaf, and d lambda will end up being a subsheaf of this. Yeah.
So the differential operators of order 0 is O of x, and the differential operators of order 1, are you saying that's just sections of the, just these dv's?
Yeah, so differential operators of order 1, they're a little bit tricky to, they're not going to be all of these. I guess it depends on the twist, what exactly they are, but you should think like intuitively, these are kind of what they are. So like over a small affine open, these vector fields will be the differential operators of order 1, but globally they'll be a little bit different.
It's I think vector field plus a function even is like, right. I think an order 1 differential operator is like a vector field plus a function, but locally.
Oh yeah.
Well, is it like sections of the either tangent or cotangent bundle twisted by
plus, so like the filtration.
Plus the O of x.
That is a filtrate. It's like Taylor series, but
Yeah.
plus it would break as OX plus tangent bundle or cotangent bundle.
Yeah, I think tangent bundle.
But it probably
Symmetric. It's a symmetric algebra on like the tangent bundle actually, because
right.
Yeah, like maybe that's a good thing to say. Like if I so this will be some non-commutative ring, but if I take the associated graded, which is a commutative ring, then I'll get functions on the cotangent bundle, which functions on the cotangent bundle are like the symmetric algebra on the vector fields.
this is like in the differential operators on the line. If you have C of x delta x del x, you take these, that's filtered by the degree of del x, and you take the associated graded, and it becomes a commutative ring in two variables at C of x, y, and that's just.
So what is the commutative ring here? Sorry.
Oh yeah, so the associated graded, so the associated graded of d lambda. So d lambda is some non-commutative ring, but the associated graded is the ring of functions on the cotangent bundle of x. And the ring of functions on the cotangent bundle is the symmetric algebra in like the vector fields on x.
Now is that twisted? Now that I don't.
Then yeah.
Is that twisted by lambda here? In
Yeah, so that's the interesting thing. So d lambda is twisted, but I think the associated graded doesn't see the twist. So that's the kind of convenient thing. So the associated graded of d lambda doesn't see the twist by lambda.
Right, so just the way to think of it is like a vector field is like a degree 1 function on the cotangent bundle.
Uh-huh.
But vector fields don't commute with functions. But if you do opacity associated graded, you get something that still looks like functions on the cotangent bundle, but it now commutes with functions. So it's the sheaf of, functions on the cotangent bundle.
Yeah, so, yeah, like, so I think this algebra of twisted differential operators is sort of weird to get your head around, but the sort of convenient thing about it is most of the actual proof will be working with the kind of untwisted algebra of differential operators. So even if like the twist seems somewhat confusing, as long as you just think of D, you won't be like led to astray, which is very convenient for us. Like really the only reason we're twisting here is because we want to incorporate like different u lambdas. But if you're happy to consider just chi subscript negative rho, then you don't need any twisted differential operators. Yeah. Yeah, and so once you have like this algebra of twisted differential operators, you can consider algebras over it, which are like quasi-coherent sheaves with an action of d lambda, and those are called twisted D modules. And
Sorry,
then
I'm still confused. So can you put like L everywhere there's a U, is that right? Like you're defining a sheaf.
yes, yeah.
But then what is L? Is L a map from L lambda restricted to U to L lambda restricted to U?
Yeah,
Or
sorry.
is it
So L should be like a section of this endomorphism sheaf, which a section of this endomorphism sheaf is the same thing as an endomorphism of the sheaf L lambda restricted to U. Yeah.
Okay.
Yeah, so yeah, sorry. So I guess I just defined it globally, but yeah, so like yeah. So maybe I'll say as a function. And yeah, so we have this category of D lambda modules.
Hold on, now I'm confused. It's a global section or it's just a local section?
Oh, so U is just my word for open set, like X is the full space, and then U is just some random open. So like I'm saying a differential operator. So I'm defining a subsheaf D lambda
It's a section.
of end C L lambda. And I'm saying that sections of D lambda over the set U are elements L in NCL lambda of U obeying some weird property. Yeah. So like X is my entire space, and then so these aren't global sections, like U is just some open. So I'm defining like a sheaf. So then I have some category of D lambda modules, and I can take global sections of D lambda modules, and then I'll get modules over a ring, namely the ring of global sections of D lambda. So I have a global sections functor that gets me from D lambda modules to modules over this ring of global sections. And the first part of Beilinson-Bernstein localization is this kind of observation that there's an equivalence of categories between this and the category of U lambda modules. And it comes from, in fact, an isomorphism of rings. D lambda of X is isomorphic as a ring to U lambda. So the kind of first observation of Beilinson-Bernstein localization is that global sections of the sheaf of twisted differential operators are the same thing as this ring U lambda, which allows us, like a priori, we just have this global sections functor that takes a D module to a module over this ring. But Beilinson-Bernstein localization is really about this functor. And so the kind of first step is the observation that these two rings are isomorphic. Yeah. And I'll say that maybe like the reason the Lie theory isn't so relevant is in some sense the proof has two parts. Part one is you verify this functor is an equivalence of categories, and part two, you verify this ring isomorphism. And in some sense, like most of the Lie theory is kind of constrained to verifying this isomorphism. And this this functor being an equivalence of categories is kind of a more geometric statement. Yeah, so I'll start by maybe saying a little bit about what this isomorphism between d lambda x and u lambda is. Yeah, so first we should construct like some ring homomorphism between them that can be a candidate for a ring isomorphism. And in fact, call it A, there's a map A from UG to d lambda x. The way I get this map is if I look at a global section of L lambda x, these are the same thing. Oh yeah.
With this equivalence of categories, so this doesn't have any of the usual like caveats, like something being polynomic or regular. This is just a blanket.
Yeah, so this is just a blanket, so there's no there's no caveats here. Like maybe the only caveat is when I say a d lambda module, I mean a quasi-coherent sheaf. A quasi-coherent sheaf with a d lambda action. But there's none of the kind of
has to be like coherent as a DL module or something.
no, yeah, so there's no, this is the very convenient thing about this, is there's no caveats. Like, so this statement up here is really just like a pure geometric statement. And because it's going to be proven in some like very geometric way, there's going to be basically no assumptions that we need for this statement, which is nice. The one thing is usually when people apply Beilinson-Bernstein localization, they're not just looking at, they're usually thinking about things called GK modules. So GK modules are like U of G modules, but with a little bit of extra structure coming from this K. And you can get equivalences for GK modules, and that's where you'll start seeing like those kind of caveat words like regular holonomic being put in. But for this version, we won't see them. And so, yeah, so L lambda of x. So global sections of this L lambda are very easy to describe explicitly. They're functions from G to C, obeying a sort of transformation law that f of GB is lambda b f of G. So remember, like lambda is some character on the Cartan, but we can induce it to a character on the Borel by saying it acts trivially on the unipotent. So like global sections of the sheaf L lambda are just holomorphic functions on G that have this kind of funny transformation rule with respect to B. And now the nice thing about U of G is it acts by differential operators on G. And in particular, if you give me an element of U of G and a function from G to C, I can differentiate it by an element of U of G. And those differential operators, I can choose them to be right invariant so that they'll preserve this transformation law. And so I'll get some action of like U of G on this by differential operators. And so I'll get this kind of ring homomorphism.
So is this meant to be of like, I guess I forgot what L sub lambda actually is. But is it obvious that these are global sections?
Yeah, so
Like what?
basically this is kind of almost by definition, this is almost how you construct L lambda. Like you kind of,
What was the construction again?
yeah, so the construction of L lambda, so it's this product G times B of V. So let me say, so how do I construct a G equivariant vector bundle on X? Well, I start by taking a representation of rho. I start by taking representation of rho. And here, V will be like a one-dimensional vector space, and this representation rho will be lambda. And I'm going to define some product, G times V over B, which it's the usual product. So like a pair of something in the group and some vector modulo the relation that G comma V is equivalent to GB comma rho BV. I think is, or maybe I want to be inverse somewhere.
Yeah, I think you want the.
Yeah. So this is then some like space where I take like G times V and I quotient it by this relation. And once you've quotiented by that relation, then it admits a map to G mod B. And you can check that this is just like a vector bundle in the usual like holomorphic sense of the word vector bundle. So like very explicitly, like G equivariant vector bundles on X are the same data as representations of B. So it turns out, if you give me a representation of B, I can construct a G equivariant vector bundle. And there's an easy way to go backwards. If you give me a G equivariant vector bundle, I can construct a representation of B. And in that way, representations of B are the same thing as G equivariant vector bundles on X. Yeah, and in particular, like, it's not so hard to figure out what sections of these vector bundles are, just because the vector bundles are described very explicitly. So like yeah. Like in particular, like saying a function from G to C obeying this transformation rule is really just saying like I have a function from G to C so that it descends to like the quotient G mod B. And like normally to descend to the quotient G mod B, I would have some kind of B invariance, but here because they're glued in that kind of funny way with the row, the G invariance condition I get has this kind of lambda twist. Great.
So confused about this because usually L lambda has no global sections.
For lambda dominant, it does. That's lots of.
Yeah, but this, you're not assuming lambda is dominant.
Yeah, so usually it has no global sections because there just won't be functions obeying that transformation rule.
Yeah, but so then you can't construct like a non-zero map by only looking at the global sections if there are no global sections.
Right, but I think this definition would make sense locally too. Like you could have some B invariant, some right B invariant open set in G, and so this could be used to define local sections as well, I think.
So the description only makes sense on B invariant open sets.
I think that's right.
Yeah. Sorry, yeah, I think you're right. I think the description I'm giving, I'm only going to be proving Beilinson-Bernstein for the dominant weights. I think this part of Beilinson-Bernstein is still true even if lambda is not dominant, but I'm only going to be proving it. I'm only going to be proving the theorem for lambda dominant, and I think in this part, if lambda wasn't dominant, like this would not be great.
Okay.
Although I think, depending on how you construct things, I think maybe lambda anti-dominant is what I want. But
I think if B is upper triangular, it can be anti-dominant. That's right.
yeah, so I think
If B is
like
lower triangular, then lambda can be dominant.
yeah, sorry. So I think I'll be stating things so that lambda is anti-dominant. Yeah, so that's a good point. So if lambda is not so this isomorphism should, I believe, always be true. But Beilinson-Bernstein localization has some caveats to it. One of the caveats is lambda is anti-dominant. And so I guess I'll be assuming lambda is anti-dominant, at least when you prove that A is not, like A gives you an isomorphism.
So is it true? Do you know? I don't know. Is it true if lambda is not like this could still be true even if lambda is not?
Yeah, so this statement is true even if lambda is anti-dominant. And I'll say a little bit.
Lambda is not anti-dominant.
Yeah, like I'll say a little bit about Beilinson-Bernstein in general once I state it, like what parts you need to assume lambda is anti-dominant for and what parts you don't. I'm only going to be proving the anti-dominant form, but if you don't assume anti-dominant, you can still get some equivalences.
So for example, if if lambda was 0, that would be one example, right? Then it's the trivial one. When lambda is 0, it's the trivial one, and there's no global section except constant. Is that right?
Yeah. Yeah, because so like there won't be any like holomorphic functions on something proper like G.
Be more big.
Yeah. 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 So like if lambda is not anti-dominant, this is, you can still define this map, but it will be the 0 map. It won't like be.
Yeah, I think this definition makes sense even if lambda isn't, because you could do that L lambda of U is this, and then what you're getting for U of G is a map into every L lambda of U where U is like a B invariant open set. And so that would be a global section of D lambda of X, even though there would be no global sections of L lambda of X. I mean, that's what it looks like to me.
How many B invariant open sets?
Well, if you any open set in G mod B, the inverse image is a B invariant open set in G, and that L lambda of X. So that it's a function from some open set in G to some right B invariant open set in G to C.
Yeah, so you get a map from like, the constant G, U of G or something into D lambda, but then it might be the 0 map when you take global sections.
But even if L lambda has no global sections, what I'm saying is D lambda still could have sections. You're still defining this map, and I think that's what Michael is saying.
But I think like you'll have a map of sheaves, but I don't think this map of sheaf, like really we care about a map on global sections. Yeah.
But it's, I guess, I don't wanna, you still can have a global section of D lambda of X, even if L lambda has no sections, is what I'm saying.
Yes, yeah, but I think this map,
Sorry,
like see them.
I'm a little behind, like. What, has the map A been defined already?
Oh, yeah, sorry. So maybe I'll say it a little bit more explicitly. So if I have some element X in UG, it kind of acts, it gives rise to a right invariant differential operator L acting. So maybe I'll say L is a differential operator on functions on G. So if X is like an element of the Lie algebra G, then X generates a right invariant vector field, and I can just take differentiation with respect to this vector field to be my action. Now, since I've specified a map from G to differential operators, it automatically extends to U of G. And so I'll get some like way of associating to an element of U of G a differential operator on G. And then if I have a function f, I'll just differentiate it with respect to this differential operator. And so this is how I get an action. Like this is how I get a map from UG to D lambda X. Like these things in U of G just act by differentiation on functions on G. And global sections of L lambda are just certain functions on G. And so yeah, I guess the theorem is that lambda anti-dominant A induces an isomorphism from U lambda to D lambda X. So there are two parts to this claim. The first part is you have to show like the kernel of this map is exactly the kernel of chi lambda. And then the second part is you have to show that the map is surjective. So I won't give like a full proof of this, but yeah, so maybe I'll say the way you can prove it. So to check it descends to a map U of lambda, one can just do a direct computation because like the action is kind of defined pretty explicitly, and you can see that the kernel at least contains U lambda. And then to check it's an isomorphism, you would pass to the associated graded. And then there's something called the Springer resolution, which allows you to understand the associated graded. And through the geometry of the Springer resolution, you get this theorem. But that's maybe all I'll say about this part. Yeah, and so now, at least for lambda anti-dominant, we've seen that kind of identification. And now I can kind of state Beilinson-Bernstein localization. So Beilinson-Bernstein localization. And I'll start by stating it like a slightly more general theorem. And then I'll say what the slightly more general theorem says if lambda is anti-dominant. So the more general theorem is that the derived category of D lambda modules is equivalent via the derived functor of global sections to the derived category of D lambda X modules. So this is always true. So at the level of derived categories, I always have this equivalence of derived categories. And I'll remark that this is kind of similar to what you see happening in Borel-Weber. Actually, yeah, maybe I'll say the Borel-Weber thing in a little more detail in a second. And then if, yeah, maybe I'll say if lambda is anti-dominant, gamma X already is equivalence. And I'll say, you can already see like this kind of derived phenomena that descends to abelian phenomena when the weight is anti-dominant in Borel-Weber. So let me see. So we saw that line bundle L lambda earlier. Borel-Weber is a theorem which computes the cohomology of that line bundle. And the Borel-Weber theorem says that Well, if lambda is a regular weight, oh, sorry, maybe I'll say lambda for lambda regular, you get an equivalence of derived categories, and for lambda regular anti-dominant, you get an equivalence of abelian categories. Borel-Bot says if lambda is regular, so if lambda is regular weight, the cohomology of XL lambda is 0, except in 1 degree. And that degree is computed as the length of the Weil group element that takes lambda to an anti-dominant weight. So there's always some element of the Weil group that will take your lambda to something anti-dominant. And then the Borel-Bot theorem says that this L lambda, its kind of cohomology is concentrated in 1 degree, and that degree is the degree, that degree corresponds to like how far lambda is from being anti-dominant. So if lambda is already being anti-dominant, what this is saying is that the cohomology of L lambda is concentrated at degree 0, which is kind of like saying like it's purely like an abelian category phenomena. You don't need any derived category things to understand it. And it's the exact same thing that happens in this functor. It turns out that this functor has cohomological amplitude equal to the length of W, where W times L or times lambda is anti-dominant. And so when lambda is already anti-dominant, the cohomological amplitude is 0, and you get a functor of abelian categories. But when lambda isn't anti-dominant, like this is a genuinely derived functor.
So by regular, do you mean like row shifted regular?
Yeah, yeah.
Is that true upstairs as well?
Yes, yeah. Yeah, I think like, yeah, so I mean row shifted regular because I put the row shift in, so I mean row shifted regular, yes, yeah, sorry. I think some people will say lambda regular, but when they define d lambda, there will be a row shift here. I incorporated the row shift in my u lambda category. So for me, regular means row shifted regular, but some sources will incorporate the row shift in d lambda. So then they'll say lambda is regular, but d lambda won't mean what I call d lambda.
There's no, just to be sure, there's no row shift on.
Yeah, so there's one row shift. You can either put it on d lambda or on u lambda. I put the row shift on u lambda. Some people put the row shift on d lambda.
But on lambda, so the second statement, the Borel-Bot statement, this is a row shift at -2. So is there a row shift on L lambda now too?
Yeah, so my L lambda shouldn't be row shifted, but I think this statement is usually Borel-Bot. Like, notice I have this kind of row shifted action.
Yes.
So if you incorporate the row shift into your L lambda, then you can use the usual action. You don't need to row shift in Borel-Bot. So
I think regular means regular after a row shift.
That's what the definition
That's
is.
the definition.
I agree.
That I think bottom statement's correct at least.
yeah, like sorry. So I think like a lot of people in sitting Borel-Bot will have a row shift in the lambda. I don't, but because of that, I mean like a row shifted version of regular.
Yes, okay, that works.
Is it easy to say what regular is?
It just means off the walls of the dominant code. Inside the for if it was a partition, all distinct parts.
What do you mean by cohomological amplitude? Is that a technical term?
Yeah. So when I have a functor of derived categories, you can ask if I have something that's not like a genuine complex, but it's concentrated in degree 0, how big can its image here be? Like how many cohomologies can it have? And that's called the cohomological amplitude. So in particular, when you have cohomological amplitude 0, that's saying that this derived functor like restricts to a functor of the abelian categories. And so since this derived functor is an equivalence, when you restrict it to abelian categories, you'll get an equivalence. If you can always restrict it to a functor of abelian categories, but if like the cohomological amplitude is not 0, that restriction won't be very nice. And just because this is a derived equivalence won't say anything about the restriction unless you have the cohomological amplitude 0.
I guess the cohomological amplitude really remembers the regular abelian category itself. Like if you just had the drive category, you probably couldn't define that, I guess, because you would.
Oh, yeah. So like, because I guess, like the one thing you could do is you could say, I have the abelian category sitting in here, and then I take H0 of its image to get a functor between abelian categories. But when I pass to that H0, I'm forgetting a lot of information. And so anything I remember about here will basically not be respected when I pass to that H0 to get a functor of abelian categories. Like one way of saying it too is these abelian categories both have T structures corresponding to like the usual T structures on these abelian categories. And I'm saying that if lambda is regular anti-dominant, this is T exact.
And just like a silly question, the case we're really interested in is when lambda is minus rho. Is that right?
I think.
Satisfies this regular anti-dominant condition.
Yeah.
Okay.
Yeah. But yeah, so I think this is maybe the part of the talk where at least now we can get away from all the Lie group stuff and start talking about like the case where x equals Pn. So I said that this proof by Bezyrevnikov, Breverman, and Poseletsky was based off of an earlier argument of Bernstein. So there are kind of two parts of this theorem. The first part is that this is an equivalence of categories, which that like does require some amount of the structure theory of Lie groups. And the second part is that this functor is an equivalence of categories. And Bernstein proved that this functor is an equivalence of categories when x is equal to Pn, and instead of twisted D modules, you just have usual D modules. So maybe I'll state that a little bit more precisely now. So Bernstein proved the following. The global sections functor gamma from D modules on projective space to modules over the ring of global differential operators on projective space is an equivalence of categories. And this is, in some sense, kind of the heart of the proof of Beilinson-Bernstein localization, at least in this Bezyrevnikov, Breverman, Poseletsky approach. So the plan for the talk is I'm going to prove this theorem of Bernstein and then explain how they kind of generalized it to Beilinson-Bernstein localization. And I'll say the kind of one downside of this approach is you don't really see the derived version. One of the kind of upshots is it means it's technically much easier to do. One of the downsides is that like it doesn't kind of go as far as some of the other proofs. And also it's a little bit more computational than some of the other proofs. Like to get a more conceptual proof, usually you really need to like be proving the derived version because that's kind of the conceptual thing happening. But in this proof, there's going to be like some amount of computation you need to do. And it's hard to remove that computation. Like the reason it doesn't really generalize the derived case is because it's hard to see what to do with that computation. Yeah, so how did Bernstein prove this theorem? So there's already like a classical theorem in algebraic geometry, which says that quasi-coherent sheaves on an affine variety are equivalent to modules over the global sections of that affine variety. And the proof of that theorem really used two facts. One is that the global sections functor is exact. And the second fact is that it reflects zero objects, meaning if gamma m is zero, then m is itself zero. And if you can prove these two facts about this functor gamma, then you'll be able to deduce that it's an equivalence of categories in the same way you do it in the quasi-coherent sheaf case. So I'll be proving these two facts about the functor gamma. And then it's the kind of relevant thing to know is gamma is part of an adjoint pair. So gamma is a right adjoint. And once you know that gamma is a right adjoint, and that's and obeys these two properties, then you can get that it's an equivalence of categories. I think, yeah. Oh, I guess there's one more fact you need to know, which is that if I call like the left adjoint to gamma delta, then delta of gamma of d lambda or of dpn is equal to dpn. But this fact is kind of easy, so I won't really say much about it. But once you know these three facts, then you can prove gammas and equivalence of categories just by some kind of abstract argument. So I'll focus mainly on how you prove these two facts. Yeah. So the idea that Bernstein had was basically that if I have like a module, if I have a quasi-coherent sheaf on Pn, this is kind of a hard thing to deal with just because Pn is not affine. But Pn is very close to something affine. So I can look at this little diagram. Look at this little diagram. So this is affine space. This is affine space minus the origin. And then if I quotient this by GM, I get Pn. So Pn is like a GM, like I guess I have this GM torsor from an plus 1 minus the origin to Pn. And an plus 1 minus the origin is not itself affine, but it sits inside of this very nice affine scheme an plus 1. And the idea is that this theorem that D modules are equivalent to modules over the ring of global differential operators, that theorem is very easy to prove for affine schemes. And so we're going to try and prove this theorem by basically reducing it to the fact that it's true on this affine scheme, which is kind of obvious. So in the end, like the proof is going to boil down to taking some object here and moving it over here. So why don't we start by verifying that gamma is an exact function? So we want to check that if 0 to m prime to m double prime to 0 is a short exact sequence of dpn modules, then 0 to gamma m prime to gamma m to gamma m prime prime to 0 is also exact. So we're trying to like prove the exactness of that statement. And so we're going to start by moving everything over to an plus 1. The first step is we're going to pull back along pi. And since pi is a smooth map, and in particular it's a flat map, pulling back along pi preserves exactness. So when we take this short exact sequence and we pull it back along pi, we get some short exact sequence of quasi-coherent sheaves on pi, or sorry, on an plus 1 minus the origin. So we get some short exact sequence here. Now, there's one observation that I want to make, which is how do global sections of a sheaf like pi upper star m relate to global sections of m? And the answer is that global sections of pi upper star m, since this map pi is a GM torsor, like Pn is the quotient of the top by GM, this space carries an action of GM. And since it carries an action of GM, we can decompose this space according to the character of the GM action. So we can decompose this space into subspaces gamma L, where Z and GM acts on gamma L by Z to the power of L. And so I can decompose this, and then the GM invariant sections, aka gamma 0, these are the global sections of M. So the global sections of M are the GM invariant sections of this sheaf, which is the gamma 0 part. And so this is how I'm going to like relate a short exact sequence of global sections here to a short exact sequence of global sections here. I'm going to look at like the GM invariant part, which is this gamma, or which is the gamma 0 part. And I'll say like this GM action here, maybe it seems a little scary, but it's actually like relatively concrete. So like explicitly, this sheaf pi upper star m is formed by, well, you take O of an plus 1 minus the origin, and you tensor it over pi inverse OPN with pi inverse m. And GM acts on functions here just because GM acts on the domain. Like if I have a function f of x0 through xn, and I have some z in GM, I can define an action like this. And so how does GM act on these global sections? Well, the answer is it acts on this part, and then it kind of doesn't touch these tensor things. And so you can think like the gamma 0 part, like the GM invariant sections, those are sections that look like a constant polynomial tensored with some sections of pi inverse m. So this is kind of why you get this correspondence. Like gamma L, you should think of as like degree negative L homogeneous polynomials times sections of M. Great. So now that we have, so now that we have that, it would be nice if we could say that taking global sections here was exact. But the problem is that an plus 1 minus the origin is not an affine scheme. And on affine schemes, taking global sections is exact. But when you don't have an affine scheme, you don't necessarily have that. So now we're going to need to push forward along J to kind of move us from that affine scheme. Yeah, and the problem is that like pushing forward along J, that's not an exact function. And so we will have like some kind of derivedness here. So we have this short exact sequence. And when we push it forward by J, instead of getting a short exact sequence, we really get an exact triangle. Rj upper or Rj lower star pi upper star m prime to Rj lower star pi upper star m, Rj lower star pi upper star m prime prime. So like pushing forward along J is not an exact functor. So to get like an exact sequence out of it, we need to take this derived functor. And in particular, the fact that we have this exact triangle is really telling us there's some exact sequence of global sections of J lower star pi upper star m prime, but global sections of this sheaf are the same as global sections of that. Like taking a push forward doesn't change your global sections. So we have global sections, and we'd really like this to be short exact, but instead of a 0 here, at the end, we have global sections of R1, J lower star, pi upper star of M prime. And so now, if we pass to the GM invariant part, we'll get an exact sequence like this. And so to prove the exactness of our theorem, we just need to prove that this gamma 0 vanishes. And this we can do by a direct computation that was done very, very cleverly by Bernstein. So Bernstein had some very clever computation to deal with that. And I'll say, by the way, so this theorem that we're talking about, this equivalence of categories, is not true for usual quasi-coherent sheaves. It's only true for D modules. So at some point, we have to use the fact that we didn't just have quasi-coherent sheaves, but we actually had D modules. And this is where, this is the part of the argument where the fact that we have a D module is going to come in, is computing that this vanishes. Like in general, this doesn't have to vanish. It could be something non-trivial, but because M prime was a D module, this is where everything is going to come from. And I'll say like,
Just to throw you off track, but do you know anything about why he would have thought the history of it? Like why?
yeah, so that's actually,
It's like it's impossible that you would just
yeah, so that's a very good question.
like be able to prove this without knowing for some reason to look for it.
Yeah, so that's a very good question. So actually, yesterday, before giving this talk, I was talking to Akshay Venkatesh, and I was basically giving a version of this talk to him, and he also stopped me and asked this question. And I thought for a while, and I couldn't answer him. And then he thought for a while, and he also couldn't find a good reason to expect this to be true. So he sent me some email this morning that he, I guess, said is maybe a reason to expect it to be true, like maybe the first step towards expecting it to be true, which is that, so D modules are kind of quantizations of modules over the cotangent bundle. And so you could maybe think about a similar statement on the cotangent bundle. And I think, so he sent me some email this morning to the effect of, basically, maybe if you thought really hard about the cotangent bundle, you would get a good answer here. But another thing is like, so this property that D modules are determined by their global sections is called being a D-affine variety. And I think like, if you really had a good understanding of why Pn is D-affine, maybe one natural thing to ask is, what other varieties can you predict are D-affine? And as far as I'm aware, the only varieties we know are D-affine are Pn and flag varieties. So like, it's not a very large collection of things that are D-affine. And I don't know why Bernstein himself like thought. I once talked to Sasha Beilinson about this, and he kind of, yeah, like, so I don't know exactly what led him, like he was led to this by the Kazhdan-Lustig conjectures, but I don't know if he was led to this like independently of that. Like, I don't know if it's just he needed this to be true to prove Kazhdan-Lustig, and so he just hoped it was true and it worked, or if like he had some very good reason to think it was true, and then it just so happened to help out with Kazhdan-Lustig.
Yeah, I suspect the latter because somehow they were looking for U of G modules, and they knew like they sort of they kind of knew intersection homology was involved, and they had this whole picture there. And so what they sort of needed was this kind of thing to really be a complete picture. So they probably did need it. So I bet that is the reason.
Yeah, so like, but yeah, I think it's still a good question. Like, why would we expect projective space to be D-affine? And I don't really have a good answer for this. Like, I would very much love to know if they're, especially because like, I think at this part of the argument, maybe it seems exotic if you haven't seen like things like this before, but treating sheaves on Pn as GM equivariant sheaves on that space is like a pretty common trick in like geometric representation theory. So I don't think that's a very like big idea. But I think this computation that Bernstein did, this was like, to me at least, it's like a genuinely like very clever thing. And I don't know how Bernstein would have thought to do this. Like I could see how someone could maybe like get to this point of the proof. But I feel like once you get to this point of the proof, you'd maybe be like, well, that doesn't vanish for any obvious reason. But also, why would I expect it to? This seems like a weird claim. Okay, I'm done. Like, I don't know what encouraged Bernstein to like keep looking for some non-obvious reason why this would vanish.
Do you know what year this is from?
I don't know. So I don't think Bernstein ever published this PN thing. I just know like Bezyrevnikov, in his note on all the proofs of Beilinson-Bernstein says that like his proof was inspired by this Bernstein proof. But the only thing I could find was like Christopher Schnell explaining like in a course on D modules this proof of Bernstein, but I couldn't find like where Bernstein actually wrote this argument on.
I think Bezyrevnikov was Bernstein's student, though, I believe.
I thought he was Beilinson's, but maybe. And maybe Bezyrevnikov.
You may be right.
Yeah, like in this, I'll say in this document of proofs of Beilinson-Bernstein, Bezyrevnikov has many proofs that are unpublished that he says were like just communicated to him by people. Yeah. So Bernstein's theorem on D-affineness of Pn might have just been another thing like that, which like Bezyrevnikov was told one day, but it was never written down. But yeah, so in terms of how we do this computation, so now we're going to use the fact that everything came from D modules. So in particular, M prime was a D module, and the D module like inverse image and direct image functors are a nightmare to work with. But luckily for us, pi is smooth and J is an open immersion. And because of that, the D module push forward and the D module inverse image are exactly the same as the usual inverse image and usual derived push forward. And so actually these short exact sequences I wrote down are not only exact sequences and exact triangles of quasi-coherent sheaves, but they're also exact triangles of D modules. And like if J, and I'll say like, this is why it's very, very important to us that J is an open immersion. So when I took this derived push forward, the reason this gave me an exact triangle of D modules is only because J is an open immersion, and the D module the D module direct image functor for open immersions agrees with the derived push forward. Like they coincide when you have an open immersion. Because you might ask like, okay, if I have any smooth map, I can always like find some way of mapping the top to an affine scheme. But usually like usually when you put something in an affine, like usually if I'm, like I could, like usually if I embed something in an affine scheme, it's not going to be an open immersion. And it's really J being an open immersion that's kind of essential for this.
You said pi being, is there anything about pi or is it?
Oh yeah, sorry, pi being smooth is why pi upper star is the same as the D module inverse image. So normally D module inverse image can be a little bit annoying to compute, but pi is smooth, which makes it nicer for us. Like if pi wasn't smooth, the D module inverse image function would also like be derived.
So flatness was not enough here, smoothness.
Yeah, so flatness is enough for that on quasi-coherent sheaves, but if you want it on D modules too, you do need the smoothness, yeah. Yeah. Yeah, so now I'll say we have this Euler vector field. Yeah, so how do we actually do this computation? Well, Bernstein's very clever idea to prove that gamma 0, R1, J lower star, pi upper star, M prime vanishes, is to look at the Euler vector field, which is this differential operator. So you differentiate with respect to some variable, and then you multiply by that same variable. And the nice thing about the Euler differential operator is it behaves very compatibly with the GM action. Namely, theta acts on gamma L as multiplication by negative L. And Euler didn't like have it in this language, but Euler, the reason this is called like the Euler vector field is because Euler wrote this down precisely because if you plug in a degree D homogeneous polynomial and apply this operator to it, you get D times your original polynomial. Because I had that little T or Z inverse in my action of GM, the numbers get switched here. And so like gamma L corresponds to degree negative L homogeneous polynomials. So that's why I have a negative L here instead of a positive L. But it's this same like computation of Euler that gives us this action. And in particular, so we're trying to prove that gamma 0 vanishes. So the way we can do this is we can just show that theta doesn't have any eigenvalue 0 on the global sections of this. Because like gamma 0 corresponds to places where theta acts by 0. If we show that theta never acts by 0, then all is well, and this will vanish, and we'll have our exact sequence. Yeah. And so how do we prove that? Well, now we're going to use something particular about this sheaf. R1 J lower star pi upper star M prime is supported on the origin. So this is supported on the origin. This is just some general fact about open push forwards. The idea is that if I take that exact triangle and like restrict it to the open subset away from the origin, then it's just like the same short exact sequence that we had on that open subset. So the only place this derived push forward can live is the origin. So this derived push forward is supported on the origin, but there's a theorem called Kashiwara's equivalence, which says that a D module with closed support is equivalent to the push forward of some D module on that closed subscheme. And D modules on a point are just vector spaces, right? Differential operators on a point, there are none. So D modules on a point are just vector spaces. And so this, one can just directly see, thanks to Kashiwara's equivalence, is of the form some complex vector space, but then you take a D module push forward, so it acts a little bit funnily. So maybe I'll write it as C adjoin del 0 through, C adjoin x0 through xn v, and then C adjoin x0 del 0 xn del n. So what do I mean? I mean, you take this complex vector space V, you let x0 through xn act on V as multiplication by 0. That's just because the coordinates of the origin are all zeros. And then you tensor it by this ring. So you let like del 0 through del n act on it. And that's how you turn V into a D module. So D module is just like an algebra over the Weyl algebra. And so here we're just basically saying like the partial derivatives just kind of act freely and the xn's act as multiplication by 0. So now we have that claim. I'll look on this board. And so we're trying to prove that theta only has eigenvalues, or we're trying to prove that theta doesn't have any eigenvalues of copy, like, or 0 isn't an eigenvalue of theta, is what we're trying to prove. And we can just do that by a direct computation. So anything, any global section of that D module looks like some differential operator where alpha is a multi-index. So this is just like some composition of partial derivatives tensored with. So any element of that tensor product can be written as a sum of things like this, because those xi's all act by 0. So we just need to show that this will never vanish. Like, or actually, in fact, we'll show that theta will act on this with some eigenvalue given in terms of alpha. Yeah, so how does theta act on this? Well, if we just write it out, theta is x0, or I guess xi, partial alpha, tensor v. And you can rewrite this now by commuting the xi and the dels, and xi will commute with like del j for j not equal I, and for j equals I, there's going to be some commutator relation. So when we switch them around, we'll have del alpha negative alpha I minus 1 tensor v, where negative alpha I minus 1 minus there will be some power of del I times xi tensor v. But the nice thing for us is that xi acts on v by 0. So once we've put xi all the way to the right, it acts by 0. So this term with xi on the right in the commutator will vanish. And so we'll get this. So like, I did that kind of fast, but the idea behind the computation is really xi acts on v by 0. You really just want to put xi on the right. You have to go through some amount of commutators to do it. But once you do it, this is the kind of term you get. Yeah, and now this is just, maybe I'll say if, now I'll say this was negative alpha plus m plus 1 del alpha tensor v. So in particular, this theta operator acts always with strictly negative eigenvalues. So it acts always with strictly negative eigenvalues. In particular, it has no 0 eigenspace, and so gamma 0 of that D module has to vanish. But that's exactly what we wanted to prove. So once we know that this vanishes, then we know that this is a short exact sequence. But that short exact sequence, as we already said, was exactly this thing that we were trying to prove was a short exact sequence. So in the end, it's this kind of magic property of the Euler vector field that saves the day and helps us prove that gamma is an exact functor. Is there any questions about that? Because I'll say, like, I'm hoping that at least this was maybe the more concrete part, like we just wrote down some explicit vector field. And so, like, in some sense, if there's anything to take away from that, at least that I hope is taken away from this talk, it's probably like this kind of computation.
Yeah, it occurs to me you could try to do this like on the cone over the Grassmannian, but I guess the point is there that I don't know if this might or might not work. The origin is you have this Fluker embedding of the Grassmannian. The origin would be like a singular point, though it wouldn't be smooth, and so I don't know if this argument would fail or not. It's a cone with a point. So I don't know if that works. If the argument would work or not.
Yeah, I know this theorem is true for the Grassmannian, but I don't know if it's true for this reason. Like, I don't know if we run this argument for the Grassmannian. Yeah, that's
Like somehow. I think it would almost run through, except that the origin isn't smooth, and I don't know if that. I'm not expert enough to know if that.
Like sort of for any variety, any projective variety, right? You could do this. Nothing happened until like here. So.
Do you need to worry about the choice of vector field?
Yeah, so that's like the one thing. So what did Bezyrevnikov, Braverman, Poseletsky contribute to like get this to be a proof of Beilinson-Bernstein? They just found how to replace the Euler vector field. So like you're exactly right. We really used almost nothing about PN. Like we used that it was related to an affine variety in this kind of convoluted way that you could imagine like many projective varieties might be related to an affine variety in this way. The only thing we really used was this Euler vector field. And that is like the hard part. is Bezyrevenkov, Braverman, and Posawitsky found some analog of the Euler vector field to use for the flag varieties.
Do you know what happens with toric varieties?
So
There's a natural picture like that.
I think it's a theorem that the only d-affine toric varieties are products of projective spaces, which is kind of annoying. So like, you might expect lots of toric varieties to have some argument like this go through, but I guess in the end, it turns out that like, unless they're products of projective spaces, so that it's literally this argument, like the toric variety won't be d-affine. Like, yeah, like it really is important that I guess we had this miracle that when we took this open embedding into an affine scheme, its complement was so explicitly understood that we could find this Euler vector field to make the argument work. And now I guess I'll say, with maybe my like last bit of time, just a little bit about how you generalize this argument. So, oh yeah, I guess the one thing we haven't shown in this PM picture is why gamma m equals 0 implies m equals 0. And maybe I'll say that just because it's another like playing with the Euler vector field thing in a very simple way. So we're going to play like the same game as before. So we have some dPn module m, and we're going to show that if m is non-zero, then gamma m can't be 0. So the reason we can do this is because, so step 1, this is non-zero. Why is that non-zero? Well, because this D module will be non-zero since m was non-zero, and an plus 1 is an affine scheme. So gamma reflects zeros on affine schemes. So since this is a non-zero sheaf on an affine scheme, it has to have a global section. But global sections don't change when you push forward. So actually, we already know that gamma of pi star m is non-zero. And remember, gamma m was gamma 0 pi star m. So we know this is non-zero. We just have to show that the gamma 0 part survives. So how do we do that? Well, since it's non-zero, we know that there's some integer L, so that gamma L of pi upper star m is non-zero, right? Like if all of these vanish, then their direct sum would surely vanish as well. So there's some integer L so that this doesn't vanish. Now, theta, so let me take theta, or sorry, let me take S, some section in this kind of non-vanishing thing. And since on gamma L, theta acts as multiplication by negative L, we know that theta times S equals negative LS. So if L not equal 0.
Sorry, can you, why was theta dot s minus L?
Oh yeah, so remember, so how does GM, or sorry, what do global sections of pi upper star m look like? They look like a function on an plus 1 tensored with a global section of m. So GM, yeah, so in particular, like if I can write it as like a bunch of homogeneous polynomials tensored with sections of m. Now theta acts on a homogeneous polynomial of degree d as multiplication by negative d. So this gamma L part is just the part of the global sections that look like some homogeneous degree negative L tensored a global section of pi upper star m. Yeah, so on pi L, or sorry, so since theta acts on homogeneous polynomials as a scalar, it will act on this gamma L as a scalar. Basically, because like so it's all coming from this kind of homogeneous polynomial fact. So if L is non-zero,
But you have to sheafify.
yeah, so you have to sheafify, but this will still be like
So it's true local.
the sheafification, yeah. Like the sheafification of multiplication by L is still multiplication by L. Yeah, like I've not been very careful about the sheafification, but you can be more careful and the arguments will go through. So theta dot s equals negative ls, and if L is not equal 0, in particular, theta dot s is not zero. So what does that mean? Well, theta.s explicitly is the sum from I equals 0 to n of xi del I s. And del I s, if I have a homogeneous polynomial of degree d, and I apply, so maybe I'll say this first. So xi times del I s is equal to this thing, which is equal to negative ls, which is something non-zero. The only way this sum could be non-zero is if at least one term was non-zero. So sum del IS is non-zero as well. But the idea is that del I moves gamma L to gamma L plus 1. You might think it would move to gamma L minus 1, but remember everything is like negative of what you'd think it would be. So if L is like a strictly negative integer, then I would just keep applying delta I over and over again. Like I would just keep applying this trick over and over again. Each time I would increase L by 1, get a non-zero section of gamma L plus 1, and I just keep increasing until I get gamma 0. If L started off as a positive integer, I would rewrite the Euler vector field so that the multiplication by xi's were on the right, and then the same sort of trick would work. So if I have a non-zero section of some gamma L, then I can always, thanks to this Euler vector field, find some combination of differential operators that will move it to a non-zero section of gamma 0. And so this is kind of, so if m is not zero, then this is not zero, which implies gamma 0 is not zero, which implies gamma m is not zero. And so this is the kind of, in some sense, like if there's anything to take away from this talk, it's maybe this proof that Pn is DFI. And I think it's like, once you have the idea to use the Euler vector field, it follows from these computations. And I think it's like a very cool and clever idea of Bernstein that you can use the Euler vector field to do all these computations. So now to end, I just want to say very briefly, like how you replace the Euler vector field and this setup when you have like this kind of situation of Beilinson-Bernstein localization. So in Beilinson-Bernstein localization, we have this flag variety G mod B, which is going to play the role of our Pn. Now we're going to pull it back to G mod the unipotent radical. And that pi was a GM torsor. This pi is a Cartan torsor, which was B mod U. And so in the same way that global sections of pi upper star m decomposed according to the characters of GM, global sections of pi upper star m are now going to decompose according to the characters of the Cartan, which are these roots. So I'll call them maybe gamma lambda. So we'll get that exact same composition as before. And in the Pn proof, we were looking at the gamma 0 part. When we have twisted D modules, we'll be looking at the gamma lambda part if our twist is by lambda, which is maybe what you'd expect. So then the next question is, what is the affine variety we embed this into? And it's a theorem in general that this is always quasi-affine. I think the easiest way of seeing it is to embed G into GLN, and then you can get things done explicitly. So this always embeds into some affine scheme as an open subscheme of some affine scheme. So you can mimic the exact same proof up until the point where we start using the Euler differential operator. So then there's a question of what differential operators do you use instead? And these differential operators were first written down by Kazhdan and Lemon to prove some result about perverse sheaves. And I think it was only later when Bezyrevnikov, Braverman, and Postuletsky realized you could also make this proof work with them. So,
by the way, just to say, I think you can get, I think G mod U is like the orbit of a highest weight vector in a regular representation.
yeah, so
And then the closure of that is affine, and that's open in that orbit. So
yeah. Oh, actually, thanks.
That's how one can see that it's quasi-affine very quickly.
Actually, yeah, thanks. The only way I could see it was by embedding into GLN, but I think this is a much better way of seeing it.
Yeah, you say it again. Slowly.
G mod U is isomorphic to the orbit of a highest weight vector of a representation if the weight is regular. And the closure of that is an affine variety, and so this is open in that closure. So it's a quasi-affine variety.
Is it not singular?
Yeah.
It would be
It's
singular.
always singular. It's this thing called the base affine space.
I think I think G mod U is sometimes called the base affine space, I thought, even though it's not
It
affine.
is,
At least like Bezievnikov called it the base affine, which confused me because it's not affine.
it's also not the base. It's the-
But I guess Bezievnikov loves calling this the base affine space, so. I think Bernstein calls it the base affine space as well. Like there's some paper of Bernstein called the base affine space about G mod U.
Isn't, so can you take A to be spec of?
Yeah, so A
like,
is,
the ring can be just a unit variance of EG.
yeah, so A is O of G mod U. Yeah, and in particular, like it's very it's very easy to describe. And in fact, the closed complement. So in this proof, it was helpful that we knew the closed complement was the origin. The closed complement of G mod U is given by, so A decomposes in the same way as A lambdas. And here, the ideal generated by A negative rho is exactly the closed complement of G mod U. So the ideal generated by A negative rho. Yeah. So, whatchamacallit? Yeah, so what differential operator do you use in place of the Euler operator? And like I said, these were constructed by Kazdan and Lemon. And then, yeah, these were constructed for the first time by Kazdan and Lemon. And they're constructed in a kind of funny way. So the Euler differential operator is a sum of terms like xi times del I. And del I is the Fourier transform of xi. So if I take the Fourier so multiplication by xi is some operation, and its Fourier transform is differentiation with respect to xi. This is just like some very fancy way of saying a more classical formula, that the Fourier transform of xi times f is equal to del I of the Fourier transform of f, with like maybe some kind of constants, like probably there's some factor of I somewhere about there. So this term is like a sum of something times its Fourier transform. Now, the Fourier transform, you can generalize it, and this is, I guess, what Kazdan and Lemon did, to a group homomorphism from the Weil group to the automorphisms of the global differential operators on G mod U. So the Fourier transform, here we were viewing it as like an automorphism of the ring of differential operators on Pn. Now, Kazdan and Lemon constructed a way of turning Weil group elements into Fourier transforms on G mod U. And then, yeah, maybe for reasons of time, I'll kind of start saying less. So, what you do is you look at W0, in W, a longest length vector. And yeah, once you have this longest length vector, sorry, maybe I'll say just associated to every root lambda, or to every root mu, you can construct some differential operator P mu, and this P mu will behave very analogously to how theta behave. In particular, Bezrevnikov, Braverman, and Postoletsky computed that it acts by constants on each gamma L, and they computed explicitly what those constants are. And since it acts by these different constants on the different gamma L, in the exact same way that we use the Euler vector field to separate out the gamma Ls, you can use these operators to separate out the gamma lambdas. And so maybe for time reasons, I'll stop now, but the idea is that that exact same proof goes through once you've constructed these P mu, which was done by this like very clever Fourier transformation trick of Kazdan and Lemon. Maybe I'll end here.
Very nice, sorry, very nice, I didn't.
Thank you.
Yeah, like I think in some sense, the most important thing to remember is like the proof that Pn is DFI, and the proof, like I didn't go through it in full detail, but like really the proof of Beilinson-Bernstein localization is the exact same proof. You just work really, really hard to construct these differential operators, but then the exact same argument works. And it's a very, I think, like this argument by Bernstein is very, very nice. I really liked it.
So for the version that was used for the Kajalowski conjectures, you need to relate this like O naught, this block of category O to like the category perverse sheaves. And I mean, it seems like it is not actually a subcategory of the category view G modules that you considered, because I believe in O naught, you require the center to act nilpotently, but not by zero. So do you know if they're like some other slightly different version, or if that version is easy to deduce from this, or?
Yeah, so I don't know actually how you get the like, I don't know how you get that category O version of this. Like. Yeah, like even in this picture, the relationship with perverse sheaves is kind of non-trivial because the words regular holonomic don't show up. Like in this story, where regular holonomic shows up is if you demand to be, if you talk about K equivariant D modules, and I guess Larry was talking last time weakly versus strongly here, I mean weakly K equivariant D modules, those are automatically regular holonomic. And so you get perverse sheaves showing up when you're looking at the G. Oh yeah, so K is like a maximal compact. So I guess in representation theory a lot, instead of just G modules, people will talk about GK modules, and those correspond to regular holonomic K equivariant D modules in this picture. The basic idea is.
What's K when you have in the GLN example?
Yeah, so when you have GLN, K would be the maximal compact, which is an orthogonal group.
Which GL?
Yeah, I guess it depends if you mean like over real or complex numbers. Like I could mean unitary group or orthogonal group, if depending if I'm being complex or real.
We were being complex.
Yeah, sorry. So I should say UN. I'll say like the reason I wrote O is because these GK module pictures are very relevant to real representation theory, and I guess the reason I wanted to learn about Beilinson-Bernstein localization is because there's this conjecture of Dave Vogin, which was turned into a different conjecture by Kazhdan. And then Kazhdan and Dougal Davis ended up proving this conjecture about like real Lie groups by taking Beilinson-Bernstein localization and making like a mixed Hodge module version of it. So they made like a mixed Hodge module version of Beilinson-Bernstein localization, and then they proved. So these GK modules are often just called Harishchandra modules, because probably Harishchandra was the first person to study them. And there was some very big conjecture about Harishchandra modules that Vogin made, because Vogin made some computer program which could enumerate representations of real Lie groups, but this computer program only worked, like only outputted the correct answer conditional on this conjecture. And so I guess this conjecture was turned into a different conjecture, which was then proven.
Well, if you're reading that paper, you know, you have more time slots available.